Hello, so here are video notes for unit test 4, part A, 8A. Keep in mind that all of these are going to be in week 8. The ones at the end I moved to week 9. So here I just want you to understand some of the words we're going to use. Dispersion, occur in everything. Dipole, polar compounds. Hydrogen bonds, some polar compounds. Ion dipoles, and ions. Now, that was just me introducing you to those concepts or those words. I am going to ask something about why all this is happening or how it was discovered. Keep in mind that it was hypothesized that 1 mole of anything is going to take up 22.4 liters. So 1 mole of gas is going to take up 22.4 liters. And if you're here at the beginning of class, last couple days in either class, I went through this here. There's a link here on how to get to this visual here. But let's say if there's 1 mole in here, in this closed container, it should be 22.4 liters. Based on, let's say it's a balloon, and you're filling up a balloon with 1 mole of gas. However, they found that it's less than 22.4 liters because of intermolecular forces, meaning one compound or element, or one compound molecule, will somewhat be attracted to each other, and therefore hit the sides of the containers with less force and less often. So, and as the intermolecular forces increase, the volume that 1 mole takes up decreases. Hence, if that doesn't make sense, look up why does 1 mole of water vapor take up less room than 1 mole of helium. And it is something we've gone over in class, but if you're unsure, it's something to research. So the first thing we're going to look at is dispersion forces. So the best way to think of dispersion forces is an electron. So let's say the guy is an electron and the girl is a proton. This walking is somewhat slowing down because of a brief attraction between the electron and the proton. Hence, if there's nothing there, they'll be walking as normal and walk right past each other. But all elements and molecules contain protons, all molecules and elements contain electrons, so all molecules and elements have London dispersion forces, meaning no matter how unreactive two elements are or two compounds are, there's some attraction between different ones, meaning if we have 1 helium, we have another helium, and they're flying past each other, there is some attraction between the two. And even though they bounce off each other, that attraction changes the way that they bounce or changes the way that they move past each other. And the weakest of these are dispersion forces. They occur in all compounds, whether they're nonpolar or polar. Now, this is just a brief, obvious example of why this occurs. Positive charges repel, negative charges repel, but positive and negative charges are attracted to each other. So if you have a proton, an electron like that, and another compound like this, or another element, so now this element wouldn't really exist. This would be hydrogen, but hydrogens are diatomic. So I'm going to make it helium. And we have something called a spontaneous polarizability, meaning that there's a small amount of time where even though helium is a noble gas and does not cause a attraction, there's no attraction between, well, you would assume there's no attraction, there is this time period where there is this attraction right there. Hence, those electrons of 1 helium atom have somewhat of a glimpse of the protons of another helium atom, and therefore there is a small amount of attraction. Now keep in mind London dispersion forces. All London, let's see here, as you go down the periodic table, so all London dispersion forces occur in all compounds, we know that. So you go down the periodic table, London dispersions increase. So as radius increases, so does LDS, or dispersion. I'll try to stick to dispersion. And therefore, if you don't know the trend in radius, or if you forgot it, then look up the trend in radius for the radius of a element. So I'll just do one of these here. Now, as you go down the periodic table, the radius increases. So bromine, one thing I should have mentioned is as dispersion forces increase, so does boiling point or melting point. And as we go down the periodic table, we know that the radius increases. Therefore, bromine, GeBr4, is going to have a higher boiling point than GeF4. And that's just because, let me go to the next slide to show you this. That is because GeBr, if we drew the Lewis structures, we would see that is nonpolar. If the attractions between two GeBr4s so if they have a greater dispersion force, like all these electrons here, there's more electrons and more protons, then they're less likely, it's less likely for that dispersion force to break and it to become a gas. So when water breaks, when water is a liquid and it becomes a gas, the molecules must break apart from each other. The bond in between Br and Ge does not break, but the attraction forces between two compounds does. Now here, this follows the same sort of concept. The only one I want to look closer at is, because you can always practice these, is this one at the bottom, where both of these, when you have this large carbon chain, you have just carbons and hydrogens. So this is called propane. And then the bottom one, we have 5 carbons. And we'll just assume those are all hydrogens. And which one has a higher melting point or boiling point? It's going to be the bottom one, because it has more dispersion forces. The reason why it has more dispersion forces is because it's a larger compound, therefore more electrons exist, more protons exist, and therefore the amount of dispersion forces, meaning that small amount of time where the electrons from one are attracted to the protons of the other, or vice versa, there's more of that. So that also can be correlate with molar mass. So if molar mass goes up, you can assume you have more protons because molar mass is correlated with protons. And if you have more protons, you have more electrons. And therefore the bottom one will have a higher melting point or boiling point. Again, nonpolar compounds only have dispersion forces. So this is a Lewis structure for a halogen, Cl2. Now, they would have these electrons around it, but that doesn't matter. We see that it's nonpolar, it's symmetrical. These are covalent bonds. So note that does not break. That is something I'm going to ask. That is a covalent bond, or a bond between two nonmetals, or a semimetal and nonmetal, something we've been covering. So that does not break, meaning when we evaporate water, solid to liquid to gas, that water is still the same thing. These bonds are not broken. But the intermolecular forces, hence the London dispersion forces there that I just circled, do break because they move away from each other like gas particles do. Here's just another example of what I drew earlier. We have a negative side and a positive side. Based on the Lewis structures and the success in that, I think that this probably makes sense. You have a positive side of a compound and a negative side of a compound. So I should have said at the beginning, this is dipole forces, meaning this is no longer, we're no longer going to talk about nonpolar compounds. We're going to talk about polar compounds. And that's where this dipole force, which tends to be stronger than dispersion forces, comes into play. And now here we have HCl. If you drew the Lewis structure of HCl, you draw it something like this, positive N, negative N. And we see the negative N of Cl is attracted to the positive N of H. And all polar compounds exhibit this dipole force. So remember, we started off with dispersion, and now we're on dipole. All polar compounds have this dispersion force, and they also have this dipole force that is exhibited here. So does an H3 have dipole? We can draw the Lewis structures, and nitrogen, like if I were to ask then, where label the positive negative side of the polar compound, nitrogen is stronger than hydrogen. So we have a negative side and a positive side. Because there are electrons where that bond is, there's two electrons, it's pulling electrons in that direction. And therefore, you have a negative and positive side. So I'll just do one of these. I'll do one and then the next, and then, well, I might do one more because we didn't finish them in class. But so here we got H, N, H, H. We have a negative side, and then we have another ammonia. And this is where the dipole is going to exist, right here. So N2 is a nonpolar compound. Therefore, it does not exhibit dipole forces. It does exhibit dispersion forces only. So let's draw one with methanol. I'm going to draw that bent. We have a negative charge going this way, a positive charge down here. And it is a polar compound. So we can then assume that the positive side of the methanol is going to bond with the negative side of it. And so we saw that in the lab here. Okay, HCN. So it's going to be pulled that way. Nitrogen is going to be negative. So therefore, the positive side, that hydrogen is going to be positive, and therefore that's where the dipole bond would exist. So the next thing we're going to talk about, so I skipped a slide accidentally, but is hydrogen bonds. So we're going to do some examples, but hydrogen bonds is a type of dipole. Sometimes teachers only ask if it has hydrogen bonds or not, or meaning if the dipole is hydrogen bonds. But since Alex is going through dispersion, dipole, and hydrogen bonds, you're going to have to list all three. So let's just say if we have HF, we know that this is a dipole. Hydrogen is stronger than, or fluorine is stronger than hydrogen at pulling the electrons, hence the electronegativity is higher. Hydrogen, we have a positive charge and we have a negative charge. We have a dipole here, but since it is a hydrogen and a fun, and the reason for that is FON. If you look at the electronegativity chart, or if you look at a periodic table, remember fluorine is the strongest, and I think most students know that at pulling electrons. The ones right next to it are oxygen and nitrogen. Thus, it creates an even stronger magnet. Hence, in a sense, a hydrogen bond is simply a stronger dipole force. But it contains a hydrogen and a fun, and the hydrogen is not connected to a carbon. Sometimes it's taught that it has to be connected to an FON as well, but I'm sticking to the hydrogen not connected to a carbon. And so you can practice these on Alex. Again, if it's nonpolar, it only has dispersion forces. And where's the dipole? Where's the hydrogen bond here in ammonia? It's something that we drew earlier, where we drew a dipole. So the nitrogen is the strongest, negative. Positive side would be the opposite, and that could be any of the three hydrogen sides, really, because it's a 3D molecule, but that's fine. Nitrogen, hydrogen, hydrogen, hydrogen. There is a hydrogen bond right there. And so ammonia, you would expect to have a high boiling point, melting point, and it does. It's a very, very light compound, meaning it doesn't have a lot of dispersion forces. So ammonia has a molar mass of 17 grams per mole. You're not going to find a lot of other things. In fact, I don't even know how many other things you're going to find that are liquid at room temperature that weigh so little. Water is one of them, but not a lot of other things will. There's only really a couple that are current to me right now. And so again, if it's nonpolar, so these are good to practice on Alex, it's just going to be dispersion. So I'm going to just do one Alex here, the last one, because it sort of shows the variety of it. And it's to ask, is there hydrogen bonds between the compound? Now the last one there, we know we need hydrogen enough, and we do have enough there, but every hydrogen is connected to a carbon. And carbon's electronegativity is 2.5, hydrogen is 2.1. Therefore, the pull that carbon is exhibiting on the electrons is not strong enough to make a huge dipole, thus hydrogen bond. Thus, for that one there is no hydrogen bond between compounds. But if we threw in a water, now we have a hydrogen that is bonded to another fun, or at least a non-carbon, and there is a hydrogen bond there. The one thing I will ask about is whether or not you understand the special properties that water exhibits because it has so many hydrogen bonds despite being so small. Water just has a molar mass of 18, and yet we can form all of these hydrogen bonds here. You know, all the dashes are hydrogen bonds. We can form all of these. For the size of it, forms a lot of hydrogen bonds. Now, because of this, these dashed lines become almost still when it freezes. Therefore, water expands when frozen. Now, other compounds do not do that. And the reason, again, is because water is no longer moving and flowing, meaning these are no longer just breaking and getting smaller and getting bigger and so forth. They're getting stuck. So water expands when frozen, and that shows you how important hydrogen bonds are, or the significance that hydrogen bonds can play. Or in another way of saying this, why hydrogen bonds are mentioned in its own category, considering that they are just a stronger dipole or a stronger dipole. Why are they mentioned in their own category? So other things that it has is hydrogen bonds have high surface tension. So if you look at the, if you touch the top of water or something, like bugs can walk on the top of water, and that's because of hydrogen bonds. So here, this is water, and so like a little water bug or whatever can walk across water. So it has a very high surface tension. And another thing is it has something called, so surface tension, and the other thing it does have is capillary action. Meaning, if you have a thin tube, and I showed this in class, and you put it in water, water will crawl up that thin tube, in a sense, going against gravity. And because water is technically, due to hydrogen bonds, a very, very small magnet, it is able to curl up the magnetic side that glass has, or in a capillary in a plant, or even in our body, we have capillaries. It bonds to other water molecules lining that capillary, and it rolls up. One last thing is ion dipole. So ion dipole are the strongest, but they only occur when an ion exists. So right here, we have NaCl. So something we've been writing a lot of is these dissociation reactions, Na plus Aq plus Cl minus Aq. Now, what does that Aq mean? It does not mean it's a liquid. Keep in mind, if something forms a negative charge, it would be much larger, so that chlorine is much larger. So it's not a liquid. Look at how this sodium is then surrounded by, or that chlorine, the Cl minus, is surrounded by the positive side of the water molecule. So where red is the oxygen. Oxygen, pulls electrons towards it. We have negative and we have positive ends. And so the hydrogen is pointing towards the chlorine on one, and the oxygen is pointing towards the sodium on the other. That's because sodium is positive, and the opposite charged ion will be attracted to the positive charged ion. So let's show ion dipole moments for MgCl2 and water. So if we had to write the dissociation reaction for MgCl2, we have if you don't know how to write these, look at past notes or videos. We have this dissociation, and then magnesium is going to be small. I can write just Mg2 plus there, and then the oxygen is facing the positive charge. So I don't know, I would write how many specifics you would have to draw, and chlorine is going to be bigger, and there would be two chlorines, and the hydrogen would be facing the chlorine, and because the hydrogen is the positive charge side. All right, so that is 8A. Some of 8B was in 8 as well, but you'll get it. All right, that's it.